In this subsection, we're going to talk about the way applying quality metrics we discussed previously. How do we do it in a systematic way? So we're going to cover different splitting schemes of the data set that allow to estimate uncertainty of the quality metrics, and talk about statistical model comparison that allows to evaluate and see if two models are statistically different. So let's consider a binary classification problem. So we have a data set of two classes. One is depicted by red here, and another is depicted by blue points on this plot. And we divide it in two equal or roughly equal samples, training and testing. And we use the training sample to feed the classifier to train our logistic regression or whatever model we choose to train. And then let's see how accuracy metric compares on those training and testing sample. So after we train our classifier and compute those matrices, then we see that it's very accurate. But if we add testing of those on samples that hadn't been seen during the training of the classifier, the quality drops. So the reason for such drop, because the model is a little bit estimating some details of the boundary curve. Like you see on the picture, you see the difference of the samples on those two slides, and it shows the same boundary, but the data set, although sampled from the same distribution, is a little bit different. And the model picked unnecessary differences, maybe somewhere in the center, that have no physical meaning, or it's just a feature of the random selection. It's not a real property of the distribution that has produced this data. And this usually leads to overestimation of the accuracy if we measure it only on the training sample. And the larger difference between the metrics on the training and testing sample, the larger model is overfit to the data it has seen during the training. So in two fractions, train and test X, train and test Y. Usually you divide it randomly, and usually train size is larger than the test size, and typical proportions are 1:1 or 2:1, and the larger the train sample size, the better the model fit. However, the larger the test sample, the more accurate quality measurements is. So it's a kind of a trade-off that one have to stick with. And the problem with this approach is that still a large part of the data is not used for the model training, and such approach may not work well for a really small data set. When omitting like 1/3 of the data would significantly decrease quality of your model. So even more rigorous approach involves adding one more sample that is called validation. And basically we train our model on a train sample, then we estimate quality of the model on the validation sample during different iterations of the training, and then only once we estimate final quality of the model on this testing sample. And approach that is more favorable in cases of small data samples is called cross-validation. And it's based on the k-folding scheme. When you split your data into k-folds and you pick one fold as a validation and the rest of folds you pick as training one. And you run this procedure k times, picking validation fold every time differently. So, and you assess the performance of the model on the validation sample, and you get the performance number, k performance numbers, and then you average those, and this would give you like mean accuracy of your model. And also you can estimate not only mean value, but also a standard deviation that would give you like degree to which extent the quality metric may vary of your on the given data. And the pro of this model is that more data is used to fit the model. So it's like k minus 1 divided by k fraction instead of 2/3 or 1/2. Although it is a time-consuming scheme because it requires to fit not a single model but k different models. For smaller data sets or for data sets that are imbalanced in terms of either labels or some features, well, labels probably is more important. You want to keep the balance of the selected characteristic for every fold that you have. So you see that the fraction of male and females is preserved across the folding scheme, which is not necessarily the case when you apply a random k-folding. And even a more sophisticated approach that is like ultimate k-folding scheme is called leave one out, when you pick as a validation set a single element and you train your model on every element of your data set but this one. So you end up with training of n, where n is number of objects in the dataset models, and then you average those models. So it looks like extremely expensive, but in case you have a really small data set, it might be a meaningful thing to do. Another leave p out scheme, it's similar to leave one out, but removes p objects instead of one. So it's basically similar to k-folding and leave one out. So another approach is called bootstrap. So you have original sample of size n, and bootstrap means that you randomly pick n elements out of the sample with repetitions, and you create certain number of those bootstrapped samples, and you use it for training your model and then for estimation of the quality of your model. So look at the example. You have the data set of 10 elements, and then you create 3 bootstraps, and you see that there are repeating indexes like x2, x2, x8, 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 etc. And also you pick a randomly selected test sets for every bootstrap element. So here is the formal description of this algorithm. here we measure the quality of the model on the objects that are not represented in this bootstrapped subsample. And then we can estimate mean and standard deviation of the quality estimate. So how do then we assess the uncertainty of our quality estimates? We have this table from the previous example. One of the ways how we can estimate this uncertainty is bootstrap. So it is similar to bootstrap out of a bag, but here we train a model on a training sample, and then we pick a test sample, and on this test sample we build B bootstrapped subsamples with n objects. And for those B subsamples, we estimate some quality metric, and we compute the mean, the variance, and we can compute the confidence intervals of this metric. The pro side of this approach that it doesn't require to feed the model several times. So we feed it only once. We just see how performance of the model varies on different subsamples of data it hasn't seen during the training. So here is the estimation. So the training error, the testing error or accuracy, and the bootstrap. Cross-validation based methods are k-folds and out of the bag bootstrap. So in those methods, uncertainties can be estimated using values for k-validation folds, and in out of bag approaches the same can be done using metric values from all the iterations. Although those methods require to feed model several times. So k is usual number, but it shouldn't be high in real life. So it could be maybe 3, maybe 5 in realistic examples. It already will be better than regular train test split. So let's look at the way how you can statistically compare if two models, although showing similar performance, can be treated as equal or as different. So imagine we have two classifiers. For one, we have accuracy equal to 0.892, and for the second equals to 0.890. And we want to see if one model is statistically better than the other. So, for this example, we cannot rely on this just variance estimation, because it's not obvious if it's better or not, because they somehow overlap with each other. And we can imply a so-called resample paired t-test. So given two models, and we choose a number k and randomly split data into train and test sample, and we feed A and B models to the train sample. And then we compute quality metrics, QAI and QBI for the model on the test sample. And then we compute the following statistics assuming the null hypothesis that the models have equal quality. So here Q subscript I is the difference between the qualities, and Q overscore is just a mean value of all the qualities that we have in this estimation. So given estimated t statistics, we compute p-value for this statistic using students' distributions for k-1 degrees of freedom, because we have k-1 independent samples. And we compare this p-value with the chosen significance level, which is usually selected as a 0.05. And in case the p-value is smaller than this significance level, the null hypothesis can be rejected. It means that performance of one classifier is significantly better than performance of the other. And we can choose the one with the best performance. Otherwise, we can claim that those models perform equally. So in this example, we can compute this t statistics, and it's equal to 1.930, and corresponding p-value for this t student with k equal to I think it was 3, with k equals to 3 in this example, and the null hypothesis is not rejected because p-value is too large for the threshold. So we can say that models are not significantly different in terms of accuracy. And there are many other methods exist that allow you to compare accuracy of the models, and there are a few examples, and there is a great tool that allows you to do this on your own, and you can explore this example, which use combined Dietrich 5x2 fold test. So here is a quiz for you to check your understanding, which cross-validation method is best for small data sets. And this basically concludes this subsection of the lecture. So we looked at the different splitting schemes and how we can apply those schemes to different cases, and looked at the statistical model comparison that allow to choose the best model that you have trained so far.